Hi, in this video series, I'm going to show you how we at Solara Technical go about defining a complete power system. I'll post these videos every week on Thursday, so please watch for them. Incidentally, Solara Technical defines, designs, and furnishes all of the systems I'm about to present, and we do so much more. Please check out our website, and if you see something you need help with, please let us know. While lithium batteries are making their way into smaller outdoor applications, and nickel cadmiums are also in use, most telecom and datacom battery systems are still predominantly lead acid. Lead acid batteries come in two main flavors: flooded, or commonly called wet cells, and valve regulated, or starved electrolyte models where the acid is suspended in either a glass mat or mixed into a gel. I'll be showing you three battery systems, all with the same capacity. One will be a wet cell system, and two will be valve regulated in different form factors. Here is an example of a flooded or wet cell battery system. To put some context around this picture, you're looking at a single 48-volt string of batteries consisting of 24 individual cells. Each cell is approximately 1 cubic foot and weighing in at 150 pounds. For a total system weight of 3,600 pounds or 1.8 tons, its capacity is 710 amp hours at the 8-hour discharge rate, or 89 amps per hour for 8 hours. This system is a two-tier stack with an absorbent spill containment kit and external ventilation. Wet cells are exactly that, wet. They're filled with liquid. If one were to leak, acid would go everywhere, if not for the absorbent material in the yellow tray. When a lead acid battery is recharged, hydrogen gas is produced, and for safety reasons, it must be vented outside the building. This is what the white plastic pipe is for. Here is a comparably sized valve-regulated battery system. It consists of an 8-tier stack, 3 cells wide. Each cell is about 1 cubic foot, weighing in at 125 pounds per cell, with a capacity of 700 amp hours at the 8-hour discharge rate. The total system weighs 3,000 pounds, or 1.5 tons. Basically the same physical volume as the flooded version and 15% lighter. Being a smaller footprint, its floor loading or weight per square foot is higher. No spill containment or additional ventilation are required for this technology. Here is an equivalent equipment rack with 7 battery trays or shelves. Each shelf holds 4 12-volt batteries or a single string. In this case, each battery is 100 amp hours and weighs in at 72 pounds each. Each shelf or string weighs 288 pounds. All 7 shelves weigh 2,000 pounds or 1 ton and have the capacity of 700 amp hours at the 8-hour discharge rate. Like the other 2 systems previously shown, its total weight is 55% of the flooded system and 66% of the large cell valve regulated system. Our passive optical network power design from the last several videos needed 361 amp hours for 1 hour at the 1-hour discharge rate. Battery capacity drops off as batteries age. In a controlled temperature deployment of 25 degrees C, standard design practice is to increase the initial battery size by 25% to account for 10 years worth of aging. An additional 10% design margin is added for miscellaneous, unaccounted for loads and small load expansion. With these additions, the battery system needed is sized at 361 times 1.375 for 496 amp hour at the 1-hour discharge rate. Using a 100 amp hour battery, Its 1 hour discharge capacity is 81 amp hours. So our design needed 496 amps total divided by 81 amps per shelf for 6.1 shelves or strings of 100 amp hour batteries. It's up to the designer to decide if they should round down to 6 shelves or up to 7 shelves. Next time, I'll size the 48-volt rectifier system needed to power everything. Thanks for listening. And if you need help with anything related to power, please reach out to us. It costs you nothing to chat. Until next time, have a great week.